Hi everybody, my name is Buongiorno Nardelli and I'm a professor at the University of North Texas where I teach both in the Department of Physics and the Division of Composition, so in the College of Science and in the College of Music. As you can imagine, my work is at the intersection of art and science. I do a lot of work in computational materials and computational condensed matter physics on one side, but I also do a lot of work in music. I'm a composer, and I've been applying techniques of complexity and data to music, both from the analytical point of view and from the compositional point of view. The topic of today's lecture deals with this intersection between music and science. And the title that I gave to this lecture is actually a little provocative, if you wish. It's called Music for Martians. And you'll see where I want to go with this title. So in particular, let me start with a little story. In 1977, on September 5th, so basically last week, but in 1977, the Voyager 1 was sent to space. Voyager 1 is a spaceship equipped for traveling in the basically the deep of the universe. The original plan was to send the Voyager skirting the planets in the solar system, so Jupiter, Mars, Saturn, and then slowly but surely get away from the solar system into the deep space. And it was meant to live a relatively short life, but we are still getting results, getting data from the Voyager even after so many years of traveling in space. Voyager was the one that gave us the first images of Jupiter and Saturn, and it's been a source of information and knowledge about not only the solar system but also other phenomena that happen in our universe. So there is one thing though in the Voyager that is worth mentioning for the scope of this lecture. As you see here, there are two technicians that are installing a disk on one of the walls of the capsule. And this disk is actually a gold disk where scientists and philosophers, intellectuals, the people that were behind this mission decided to put information about our Earth, and our Earth in terms of its inhabitant and our culture. And believe it or not, the main part of the data in this disk, as you can see on the right, are the sounds of Earth. So this is a list of the music and the sounds that have been recorded on this golden record. And you can check it for yourself. This is the website of the NASA Jet Propulsion Lab where this data is conserved. And you see here that we have Bach, we have Beethoven, Mozart, we have ethnic music from different parts of the world. We have jazz. We have a cross section of music in our human culture. There are also other sounds. There are sounds of animals, sounds of machines. There are other sounds that belong to our being human. But it's interesting that we have all this music in this golden disc. So let's assume that a few millennia from now, because before you get to another solar system, the Voyager has to survive for many years. But suppose that, by chance, the Voyager is intercepted by another civilization, a civilization that has a deep knowledge of math, physics, data, networks, and dynamical systems, but they lack completely the evolutionary structure that made music possible on Earth. So would they be able to understand these data that are on this disk just by looking at the data or analyzing the data without having the biological tools to understand what music is? And so this is the premise for this talk. Is there a way that we can look at music as a data system, and what are the consequences of looking at music in this way? Before we go into the discussion and the methodology behind this approach to understand music, or even, you'll see, to make music, we have to step back and introduce a different way, maybe that some of you might not be familiar with, of looking at data. And this has to do, data, as you have learned, can come in many different flavors. And in the course of this semester, you've been looking at a lot of pattern and connection with patterns and so on. I mean, those are ways of looking at data. The way that I want to introduce today to you is looking at data as a network. And this is a map that we have all seen, on the back of our magazine of the airlines while we fly from one place to another. And it's a map of all the connections between principal airports in the US. And this is for some airline, I don't remember which one. Now, what is this? I mean, what we are looking at is a collection of data, and these points, these data points, are actually the airports that exist on the US mainland. Well, actually, even in the Hawaii here. And the red lines are the existing connection flights. So this is a way of looking at the whole transportation network of this airline in terms of nodes. What we call nodes are actually the data points, the airports, and edges. The edges are the connection between these data points. Now, one thing that appears immediately from this picture is that there are some data points that are more important than others. You see here Salt Lake City, or Atlanta, or New York, Minneapolis, Detroit. These are big hubs, and we use the term hub also in the airline business. You hear the hub for whatever American is Dallas-Fort Worth. So these data points appear to be more important in a way than the others. And this introduces one of the concepts that will be central to my lecture, the concept of degree of a node. So the more connection a node has, the higher is its degree. And this degree, it's actually a quantity that is important to measure some of the properties of this network, as you will see also in the context of music, as I will introduce in a minute. And so this is the first characteristic of a network that I really want you to keep in mind while we go forward. The second characteristic of a network is better shown with this particular picture. As you see, this is again a picture that has nodes, all these little faces of people that you can maybe guess from the screen, connected by segment, by edges. So this is a social network, as you can imagine. It's actually my social network on Facebook from a few years ago, when Facebook would allow people to download the image of their network. And here we see a different kind of phenomenon. We see that there are nodes that are more connected than others, so we still have this hub structure. And so the degree of the single node is important. But also, we see that nodes are kind of clustered together in groups. And these groups are groups of nodes that are connected within themselves. So there is basically a sort of community structure in these nodes, so that they belong to the same class, the same category in some way. So in my social network, these are my friends from, say, the science, these are my friends from the music, these are my friends in Italy, these are my friends in North Carolina, whatever. So there are connections between these groups. As you can see, they are not isolated. It's not just a group of people that is staying there. But there is definitely a community structure. And this is the second characteristic that I will use in my lecture to discuss the properties of the networks that we can get out of this interpretation of music. This is what is called modularity, or modularity class, and it's a measure of how much within a network a subset of nodes are connected together and form a community structure. Okay, now we have this kind of background. I mean, it's very rough. You can read about networks. I mean, there are tons of resources, both online, in print, that you can explore if you are interested in this way of dealing with data systems. But now let's see how we can look at music as a data system, and so apply this representation of network in the context of music. So music is a very generic term, and in terms of, say, the technical aspect of music, many of the components of our perception of music can be looked at as data system. So a melody can be looked at a data point, for instance. A harmony, a chord can be a data point in this harmonic space. You can make, representation of rhythm, representation of timbre, representation of orchestration. But in this particular lecture, although I've worked on all these aspects, in this particular lecture I will focus mostly on harmony. So a very specific space, musical space, that lends itself very well for an introduction to how we can use network to describe music. And I have also to say that I will be mainly concerned about the Western classical music tradition, but and the example will be drawn by from the Western classical music tradition, but this kind of approach is actually very general, can be applied to any kind of musical form. Okay. The main, or the main primitive of music is pitch. So we know that to make music we use 12 notes from C to B, going through D, D flat, E flat, F sharp, and so on. So our representation of the individual minimal data point of music is the representation of a note. And we can represent note with numbers, with names, or with numbers, and in what follows, I will follow this representation in terms of numbers, because I will be applying mathematical operations. I mean, it's kind of under the hood, you will not see that, but from the practical point of view, we deal with notes as a number representation, so that we can actually operate on this data. So we have 12 notes. What can we do with these 12 notes? And before I tell you what I can do with these 12 notes, I want to quote from a very famous short story by Jorge Luis Borges that is called The Library of Babel. And I mean, if you're not familiar, it's a very short text. It's just 3-4 pages. And it's very relevant for what I'm gonna discuss in the following. So I quote, "The universe, which others call the library, is composed of an indefinite, perhaps infinite number of hexagonal galleries. Each wall of each hexagon is furnished with 5 bookshelves. Each bookshelf holds 32 books, identical in format. Each book contains 410 pages, each page 40 lines, each line approximately 80 black letters. There are 25 orthographic symbols. The library is total, perfect, complete, and whole, and its bookshelves contain all possible combinations of the 25 orthographic symbols, a number which, though unimaginably vast, is not infinite, that is, all that is able to be expressed in every language." So in his symbolic writing, and then Borges was famous for his self-referencing and complex way in which he was building his stories. In the library, there are all the possible combinations of 25 orthographic symbols in the form of books, most of which don't make any sense, but some of which contain, a subset of which contain all the books that have been written by humanity, and that all the books that will be written by humanity in a combinatorial sense. I mean, it's definitely, a metaphor here, but it's very interesting to look at this problem of what can I do with my 25 orthographic symbols. If I had an infinitely powerful computer, I could combine all these symbols in all the possible ways, in all the possible permutations, and eventually, among all of these permutations and combinations, there is something that will emerge as a book that I can understand. And I want to take this kind of picture and, in a way, apply it to this harmonic space. As I said, we have 12 notes, or if you look at the keyboard of a piano, for instance, you have 88 combinations of these 12 notes. And I can build out of these notes any vertical arrangement of multiple notes. So I can build what I called, in musical sense, a chord. A chord is a superposition of different notes. Now, let's simplify this problem, and let's say that we take chords where duplicate notes that belong to different octaves, are basically the same note, just to reduce the number of possible combinations. And then I have a representation, a minimal representation of my harmonic space. Now, this harmonic space is unimaginably vast, as Borges would say, because, if I start with just 12 note space, I have 4,096 possible chords that I can form out of these 12 notes. If I double the number of notes to 24, I go to 16 million or almost 17 million different chords that I can build. And if I take the whole of the piano keyboard, the chords that I can build on the piano keyboard are numbers, a number that is larger than the Avogadro number, the number of atoms in a square inch, a cubic inch of matter. So it's really an extremely large number of combinations that I can build. And so in a way, this is my library of Babel. It's like, okay, I can build all this harmonic combination and build all these chords. But can I make sense of this using this approach that I've been hinting of network representation of data? Well, the idea is the following. We have to build a geometrical model of the harmonic space where chords are basically represented as vectors. So they have a kind of form, a mathematical form that corresponds to the different notes in that chord. And by giving this vector representation, I can define a distance between vectors, like the Pythagoras theorem in this musical space. If I do this, I immediately have the components of my network representation. On one hand, I have nodes, where each chord is a different node of the network, and edges, where each node is connected to other nodes through edges that have a meaning of a distance. Now, this is still an enormous data space and would be extremely difficult to give you a graphical representation of this very complex network, because in principle each node is connected to any other node. But if we kind of distill with rules a part of this space, then we can have a better idea of how this network is made. So let's assume that we build a network of nodes where each node is connected to another node if the distance is smaller than a particular number or is equal to a particular number. Well, if we do this, and we do it only for a subset of this space where each chord is made of 3 nodes, so I'm taking really a cross-section of this enormous infinite network, and I look at only some very specific and constrained subspaces, in a way as if in the Library of Babel I was finding the shelf where only a particular set of combination of characters were in the books, I would see something like this. So I would see that for a given distance I have a space that resembles kind of a spherical arrangement of nodes. If I change the distance, I might divide my network into different subnetworks that don't talk to each other, and so on and so forth. I mean, one can do a lot of different slicing of these networks. So this is geometrically very nice and satisfying in a way, because it's some sort of map of all the combinatorial possibilities that I can build out of this 12 notes arranged as a chord. But it's still not music. So this is like the Library of Babel, an infinite or almost infinite combination of data points that by themselves don't have a particular meaning for us as human and a human able of perception. So where is the music? Well, the music comes when instead of looking at this complete networks of all the possible combinations of notes, we move away from this picture and we introduce what I would say the complexity through the hand of the composer. And in a way, this is a probabilistic way of introducing an order, some sort of order in this chaos of all the potential combinations. So the composer is the one that out of this infinite number of possibilities extracts the ones that probabilistically or according to some generic rules make sense to her and build the composition out of these choices. Like the writer, in a way, chooses only combination of 25 characters that correspond to words in their own language, and then combines these words according to rules of grammar and syntax and build sentences that make sense in their own language, and out of the sentences they build a book that makes sense and has a story and has a scope that is beyond the combinatorial aspect of the full Library of Babel. To illustrate this concept, I now want to show you one of these network representations of a very simple piece of music. This is a Bach Coral from one of his cantatas, and Bach chorals, in the world of music theory and musicology, are some sort of kind of a very prototypical data set. Is what in data science would be the iris petal data set. That is kind of the reference for when you start learning about data, and data analysis is one of the first set that people use. So this that you see here is a network representation of one chorale, the one that is listed here. And before I discuss more of the structure of this network, I want you to listen to it. So what you have seen here is the evolution of the composition, so the evolution of the chords from in this piece of music, where each chord was highlighted by this red circle anytime it was played in the course of the execution. So you see how this the piece evolves around different centers, and here the concept of degree comes again in the picture, very important here. There is there are regions where the composition kind of stayed for specific amount of times, and these regions are very well identified by different colors in this map. And it happens that the colors are actually decided on the basis of the modularity class, this concept that I was introducing in the context of a social network, this belonging to the same group in a way, a measure of this homogeneity within a particular group. And the very interesting aspect here is that these different groups, the blue, the cyan one, the green one, the pink one, they actually correspond to different keys in which the piece is played. So it starts from the key of E major, then it goes in F sharp minor, and ends in F major. So it's a representation of the harmonic structure of the piece that is not imposed upon the network, but is a characteristic that emerges from this network. So from this network representation, we learn that Bach was using rules of harmony that allowed the progression of the piece to go from one key to another. And so by giving this representation, we are actually inferring from the network structure, so the topology of this network, some internal characteristics of the music itself. So this is, I think, an extremely powerful first example of how this network representation can be used for a deeper understanding of some of the structures that exist in music. In this section of the lecture, I will focus more on the problem of tonal harmony and how we can basically expand this idea that the network topology informs us about some of the inner structure of the music, the structure that has been used to produce that music, in a more articulated way. And this also will allow me to introduce a little bit more the way in which this analysis is done. How do we get the data from the music, and how do we analyze this data in a complete sense? So what I will be using for this particular example is a string quartet by Beethoven, the Opus 127, the quartet number 12, where I have here the first page of the score. I mean, even if you don't know music and if you don't know how to read a score, really the piece of information that I really would want to you to get home with is that if I look at this score, at these symbols in this vertical sense, all this vertical superposition of notes are chords. So each of this vertical superposition of notes can be mapped to a vector, as we were saying before, and these vectors themselves are nodes of this score network, where connections now are connection between vectors that are adjacent to each other. So I have a node between an edge between this chord and this chord, and I have an edge between this chord and this chord, between this chord and this chord, and so on. So this is the way in which the network is constructed. Now, if we look at this network from the point of view of the network topology, the network geometry, there are various aspects that we can point out immediately. So first of all, again, we see a degree of certain nodes that is way higher than the degree of others. So you see that this E flat major node is very connected, as it is the C minor node that is very connected. Other nodes have fewer connection. I mean, you know, this node here or this node there, they have very few connections. And here the degree is also represented by the radius of the circles. The larger is the circle, the higher is the degree. So there is a property that we could call centricity that is associated with the degree distribution of the nodes. The other thing that we can see immediately is that there are basically three colors in this map, in this network. There is kind of magenta, yellow, and blue. So what basically this means is that there are three main modularity classes, and that means that there are three main chordal community, harmonic communities, and this corresponds to the different keys in which the piece evolves. I mean, it starts from E flat major, then it goes to G major or G minor, and then I mean, there is a whole evolution that we will see actually better in the following discussion. There are two more things that we need to observe. So if you notice, all the edges in the network have arrows. That means that the edges are directional. In the piece, the composition, Beethoven himself goes from one chord to another in a given direction, but not in the opposite, for instance. So there are instances in which the piece goes from say E flat, G, B flat to A flat, D, A flat, C, E flat, for instance. So there are but not vice versa. So there are cases in which this relationship between nodes is one directional. And moreover, there are relationships between the modularity classes and the degree distribution. So the connections between the modularity classes, so the communities within this network, are linked to this degree distribution. So the degree distribution of the hub is such that that particular node, that particular chord serves as a connection between two groups. Well, so it happens that these four characteristics are actually the characteristics of the tonal harmony, the harmony of the music from, say, the 1600s until I mean, in the classical Western music world until the beginning of the 20th century, but is the structural musics, the structure of the harmony of pop music, the structure of the harmony of jazz music, and so it's basically what we listen more in our daily lives is music based on tonal harmony. And so the four characteristics that I discussed before in this geometry and topology of these networks are characteristics of tonal harmony, because tonal harmony is governed by few central chords. The chords occur in a hierarchical structure. There is a preference for asymmetric chord progression, and this hierarchical relationship exists at every level of the composition. All this can be directly linked to the properties of the nodes as in terms of their degree and their connections and their belonging to the same community or the same group. What we have seen so far is a representation of the score of the music as a static data system, but we know that music happens in time. And not all the chords are played at the same time. There is a progression. You go temporally from one chord to the next chord. And so this opens up a different way of looking at the score as a time series rather than a simple network in this sense, where now I can represent the score itself as the occurrence of a particular chord at a particular time. So this is basically the representation of this score in terms of its data points, its nodes, seen as a time series. Well, we can look at the time series as basically a dynamical process. It's the process in which the score evolves from the beginning to the end. But the interesting aspect here is that we can look at time series from a statistical point of view, from a data point of view, as segments of similar behavior. And the segments can be inferred by using specific algorithms that I don't discuss here at all, but that allow us to identify regions of time where the system behaves in a kind of coordinated way that is basically as if it's all within the same community. And so if we do this kind of analysis, we end up with a network representation of the music, the piece of music that becomes dynamic. So now instead of having a single network, we have an evolution of different sub-networks in a way that give us a snapshot of the behavior of the music in a particular region of time. And so here you see that we start from a particular community group that correspond to a particular key, that in this case is E flat major, and then upon a transition we get to a region where now the key is G minor, and nodes that were important in say one region, like here, are no more important in this region, in this layer here of the network, because now the most important node is changed because of the change in the characteristics of the music. And this one can be seen even better here, where this is our E flat chord, major chord, that is the key of this layer, that becomes kind of a pivot to transform into, to translate into a new key that is now G minor. And you can do this for all these subnetworks. So in a way, combining this representation of networks with a time series analysis, so with the dynamical process of the evolution of the score, we can get a lot of information about the structure of the music itself and the rules that the composer has imposed upon this, infinite number of combination and choices that he had. Beethoven, when he wrote this piece, he had basically all the almost infinite number of combinations that he could have used for the chords and the chord progression, but he chooses these particular ones that reflect, in a way, his conception of music theory. And so we see here that this conception, this basis, the conceptual basis for the composition of this piece emerges as a property of the network itself, and this is something that can be used to perform analysis and even to write compositions based on these ideas. I now want to touch upon another aspect of networks, and one that is actually interesting from the point of view of the composer. So I have all this, developed all these ideas of network representation and musical spaces and so on, but I showed you only the application to the analysis of a composition, but I didn't talk about if I can use this as a means of writing a new composition. I mean, of course it is, because I can always construct a network and then use it for composing. But are there ways that we could do this in a kind of semi-autonomous way, for instance, where we let the system, the computer, for instance, find the solution of the how to navigate this network in a way that makes sense from the musical point of view. And so this is the problem of finding a path through a network of chords. And something that can be illustrated very simply with one of these Bach chorals from this large databases of chorals that we can use. This is another one, but it's not the same that I played at the beginning, but the concept is very similar, and actually you will listen to it in a moment. So the idea is to find the path through this nodes and edge structure that gives us the minimal length of path, the optimal solution to go from one node to another, going through all the edges at least once. Well, this is a well-known mathematical problem. It goes with the name of, it's part of the class of problems that go with the name of route optimization problems. It's the problem of, this is a general class of problems that goes under the name of route optimization problems. Is the problem of the delivery driver that has to go through a neighborhood and all the houses of the neighborhood. What is the most efficient way of go through all the different houses and so on? We can apply this to this particular score network, and what we get is that actually the solution of the route optimization problem and Bach's version of the chorale are basically very similar and very close to each other. Bach repeats a few more times some of the transition from one chord to another, but the structure of the network is very similar. So we can in principle use this as a means of composition. So for instance, what we could do, we could generate a network that has the characteristics of having hubs, nodes that have more importance than others. So we follow this kind of knowledge that we extracted from the analysis of a tonal piece like Bach chorales or the string quartet by Beethoven. we build this network using some probabilistic and statistical ways. We assign the chord distribution according to this the degree distribution that we have already measured, and eventually we end up with a route through all these nodes, through all these chords, that we can use to compose. And so, as an example now, I want you to listen to the original Bach Coral, the one that I use for building this network and whose degree distribution I use to build this network, and a synthetic chorale that is built by using the progressions that come from a synthetic network, one that has been generated with an algorithm that has been designed by two pioneers of network science, Laszlo Barabasi and Reka Albert. And so let's listen to these two examples. And now the synthetic one. So you can hear that there is a difference. These are not the same pieces, definitely. The second one, the synthetic one, might have some, chords that are, they might sound a little bit more modern than Bach, but the structure is there. It's still very tonal. It's has an evolution that is in a way compatible with the what we observe, we hear in the Bach's piece. So this is an interesting avenue for designing agents of autonomous composition, for instance, by extracting specific rules from the analysis of the corpus of a particular composer, and then using those rules, those statistical distribution of probabilities and these networks that can be built with these ideas for the composition of a different piece in the same style or in the same verve of the original composer. Now, there is something more scientifically profound, if you wish, that we can work once we have this kind of representation of music, and that's has to do with complexity and representation of complexity and universality in the music space. So just a few thoughts on this, and this has to do with the idea of entropy and information. Basically, the representation of a data set through a complex network basically gives us a map of the communication of information, because we encode what are the structure of the allowed messages, and basically it gives us a way of analyzing the dynamics with which we communicate with one another, and in this sense how music within itself communicates within the different aspects of the composition, for instance. So one of the things that we, as scientists, as physicists, we want to really understand is if I mean, we know that we can measure. We can use entropy as a measure that characterizes the property of the network topology. It's interesting to use entropy as a way of quantifying the information that is encoded in the network, and this basically gives us a correspondence between the structure of a score, for instance, and the way in which the information is encoded in the score through the entropy measure. So I don't want to go into any of the details that we have been starting to look at in order to address this specific problem, but what I want to show you is an example of a measure of complexity through time. So these are measure of complexities in Western classical music, going from Josquin-des-Prez, so late 1400s, to Mahler, that means early 1900s, going through the different stages, eras of Western classical music. We have Renaissance, Baroque, classical, and more kind of romantic and post-romantic styles. And you see here that it seems that complexity increases with time, and this has to do with the way in which chords are connected with each other or how chords are built. So there is more complexity in the way in which chords are built, say, in the post-romantic era than it is in the Renaissance, for instance. And just out of fun, this is the same graph but superimposed with some of more popular music that we are probably all familiar with. And it's interesting to see how Michael Jackson Thriller, it's basically aligned with the complexity of Palestrina, while Frank Zappa seems to be the most complex of all in this kind of representation. All the tools and the codes and also some of the data sets that I've been showing you in this lecture are free and open source, and they can be downloaded either through GitHub or PyPy. This is a large Python library for classification and the manipulation of sequences, generation of networks. There are some deep learning algorithms for timbre recognition and also sonification of arbitrary data. So there are some papers, I have to say 2 of them in press and some of them already published that deal with these problems in more depth, that you are welcome to check out and see for yourself. They are all available through the archive. So let me conclude by going back to our alien civilization that got the golden disk and was able to extract all this information out of it. Now networks, degree distribution, I mean, they can't hear, they can understand what they hear, but they have all this deep understanding of data, and now they have a very good idea of what this data looks like and what are the implications of these data structures. So if you remember, late last year, there was this detection of a mysterious radio signal from a nearby star, Proxima Centauri, and people were saying, "Oh, could it be an alien civilization that is sending signal to us?" And so, I mean, kind of to conclude this excursion into music and data, why not this radio signal was actually music from Martians, from an alien civilization. And so maybe in the structure of this data, we can learn more about civilization in other parts of the universe. Thank you very much, and if you have more questions, please feel free to send emails, connect through my website, and where you can also find more about my activity as a composer and media artist. So thank you very much for your attention.